Even if your only memory of prime numbers is just struggling through grade school math, you've probably just accepted the idea that they're, well, kind of unpredictable, random, right? But today, we're diving into an explainer of some source material that is going to fundamentally shatter how you look at one of math's oldest mysteries. We're going to unpack a groundbreaking framework known as the prime field architecture. And what this reveals is that primes absolutely aren't just some random scatterplot. They are actually gears in a highly structured, dynamic machine.
For literally centuries, traditional methods, like the famous sieve of Eratosthenes, have treated finding primes as this chaotic, static elimination game. You cross off the multiples of 2, then 3, then 5, and whatever happens to be left over, well, that's a prime. But what if they aren't just leftovers? What if they are predictable gears in a vibrating machine? Instead of just crossing numbers off a list, we might actually be looking at a complex arithmetic engine that generates measurable frequencies.
So here's our roadmap for how we're going to break this all down. We'll start with the Mod 30 foundation, move right into the 3' field fibers, and then explore symmetry and infinite motion. From there, we'll get into the actual arithmetic engine theorem, seeing primes through FFT, and we'll wrap it all up with the modular phase lemma. All right, let's jump in. Starting off with Section 1, the Mod 30 foundation.
Now you might be wondering, why the number 30? Well, 30 perfectly frames the boundary of this entire system. Think about it. If you multiply and remove the first 3 primes, 2, 3, and 5, you get 30. That locks in a beautifully repeating cycle spanning from 0 to 30. This Mod 30 base acts as the absolute positional anchor for the whole architecture, and it gives us exactly 29 active positions to classify inside every single cycle.
Moving to Section 2, the 3' field fibers.
Okay, once we have that Mod 30 base, the field cleanly separates all the numbers into distinct lanes, or fibers. We're going to set aside the P2 fiber for a second. That's just the even numbers, so we can really focus on a fascinating contrast. On one side, you have the P1 fiber. This holds the primal candidates. These are 8 specific positions perfectly co-primed to 30, meaning they share 0 common factors with it. On the other side, we have the P3 fiber, which catches the composite odd numbers. And right smack in the middle of that P3 fiber is position 15, which acts as a fixed seam that just perfectly bisects the entire field.
Next up, Section 3, symmetry and infinite motion.
But this isn't just a static, frozen wheel. This brilliantly illustrates how translation and reversal symmetries actually inject motion into the system. First, every single number pairs with its complement. For instance, 1 pairs with 29, 7 with 23. It is perfectly elegantly balanced. Then, by just adding multiples of 30, we translate this exact structure infinitely forward through space. This reversal symmetry, where it reads the exact same forward and backward, combined with continuous translation, carries these finite prime fibers endlessly forward, all while maintaining perfect geometric balance.
And this right here brings us to a massive paradigm shift from the source material. We have to completely stop thinking about this as just categorizing numbers into static bins. We are actually observing a dynamic engine. When larger parent primes, like 7, 11, or 13, start eliminating candidates in our P1 fiber further down the number line, they aren't just crossing off numbers on a chalkboard. They are creating real mechanical disturbances in the field.
Let's look at how that works in Section 4, the arithmetic engine theorem. You can almost think of this as a measurable tug-of-war. We define 2 opposing fields. First, the survival field, which measures the candidates that haven't been eliminated yet. Second, the disturbance field, which tracks the cumulative elimination events every time a parent prime successfully knocks out a candidate. As we move infinitely down the number line, survival decays and disturbance grows, and it does so deterministically. Those parent primes sweep through the Mod 30 blocks, striking their targets in a perfectly predictable periodic rhythm.
Which takes us to Section 5, seeing primes through FFT.
If this is truly a mechanical engine, we should literally be able to measure its vibrations, right? Well, by applying a fast Fourier transform, or FFT, to our survival field data, we can filter out the overall downward trend of that survival decay. And once we strip away that background noise, we discover something absolutely incredible. Primes actually possess measurable, periodic frequencies. They operate exactly like harmonic waves.
This spectral decomposition is just breathtaking. When you map it out, you see dominant power peaks perfectly aligned with the frequencies of our parent primes. The absolute strongest frequency pulse is exactly at 1/7, the next strongest pulse is at 1/11, and the next at 1/13.
I mean, the primes are literally broadcasting at frequencies directly tied to their own mathematical value.
Finally, Section 6, the modular phase lemma.
Now, the math definitely gets a little heavy here, but simply put, this lemma proves that a prime candidate's physical position on our mod 30 wheel exactly dictates its timing or its phase offset inside the engine. It uses a mathematical operation called modular inversion. Basically, the arithmetic geometry translates directly into the phase of a physical wave. But the real question is, how well does this hold up to reality?
When we look at the empirical data comparing the mathematically predicted phase to the observed phase across hundreds of thousands of integers, the alignment is shockingly tight. For example, if you check paired prime 11 and residue 11, the error between the theoretical prediction and the actual observation is just 0.006 radians. Across the entire board, the maximum error is consistently less than 0.03 radians. Honestly, that level of precision is just astounding.
In fact, for the parent prime 7, the circular correlation coefficient between the theoretical math and the empirical observation is a staggering 0.998. In statistical terms, that essentially means the mathematical prediction and the real-world behavior are virtually identical. The physical geometry perfectly dictates the frequency phase.
So what is the big takeaway from all of this? It's that the mod 30 prime architecture isn't just some random scatterplot. It functions exactly, and I mean exactly, like an arithmetic phased array antenna. The parent primes act as the frequency broadcasting sources, the mod 30 structure acts as the propagation medium, those residue channels are the receivers, and modular inversion supplies the precise phase geometry. It is a fully functioning, measurable mechanical system constructed purely out of integers.
It's an unbelievable shift in perspective, isn't it? It leaves us to wonder if the very foundation of mathematics, which we've pretty much always assumed to be somewhat chaotic, is actually this highly tuned, vibrating machine. Well, how many other random systems in nature are just waiting for us to find their underlying mathematical engine? What else in our universe is broadcasting a frequency we just haven't tuned into yet?